Hello. So I had intended this to be a live class, obviously, if possible, but life sometimes doesn't go as planned, and I got to COVID. Same with me and my son. So not feeling 100%. Not sure how I'll feel later in this week. So I wanted to record this video while I had the energy to do it. And if I feel better this week, that's great. If I don't feel better, then you'll have this. And even if I do feel better, unfortunately my son will have to be home all week, which means that someone's got to take care of him, and that person is going to have to be me, which means I won't be available in the days for the classes anyway. So thankfully, you have this OHS training come Wednesday, Thursday, Friday, so maybe that's a blessing. In any case, I'm going to try to get through the rest of the whole unit in this video. And you can take it bit by bit. You don't necessarily need to work through this in a single sitting. If it feels better to you to split it into multiple sittings, then that's what you should do. But we have so little left in the unit that I just wanted to finish it off. And fingers crossed I'll be able to have a live class with you before the end of the semester. But we'll see. So this is page 20. I was going to show this in class. I was going to work through this question in class, how we can use U substitution in an application question, but that's probably not the best choice at this moment to do an extension, just in terms of my energy levels and everything. So I'm going to skip it, but if you want to see how it's done, please look at the answer key, which I've always got posted online. And if you have any issues with it, or you're curious how something's working and you're not sure how to work it out, please contact me and I will make it a priority to get back to you. So this is page 20, and page 21, same deal. It's the extension, and we're going to skip it, but I have done the full solution online if you want to take a look at the answer key. But let's get into the final topic of Math 1140, whatever the name of this course is. Which is the definite integral. So the definite integral, definite integral and area under the curve, those are two ideas that are related. Let's try to, come on, there we go. Definite integral and area under the curve. So I'll read what it has to say, and I'll set up this final topic, and hopefully it'll make some sense to you. So using derivatives, this is before we started integration, unit 4 or 3, 4, and 5, we were doing derivatives. So using derivatives, we were able to find the rate of change of a function. So not talking about integration here, talking about derivatives. Back in the day, we were finding rate of change, which again is, d by dt, for example, stuff like that, or d by dx. That's our derivative. By using integration, apologies for my voice today, by using integration, we are able to find the area under a curve of a function by using what is called the definite integral, whose formula can be found below. So to make sense of this, let's look at the diagram of a function f of x on some interval a to b. So this means the starting interval is some x value where x is equal to a, and this ending interval is some other x value b, some endpoint, okay? So to look at this diagram, the area under a curve is basically the space from the point A to B. So if we map out, let me use a color to make it obvious. If we go from this starting point, we've got our main function, and we want to know how much space is taken up under the function, well, we can kind of say, well, what area do we care about? We care about the starting point A and the end point B. We want to know how much space is taken up by this function in like square units, whatever the units may be, okay? So normally, if this was basic geometry, we would have like a square, and maybe we would know that it was like 4 by 2, and the area would be 4 times 2, which is 8 units squared or something like that. Or maybe if we had a triangle, we would know that, it's got a base of 4 and a height of maybe 3, and maybe you'd find like 1/2 base times height, which would be 1/2 4 times 3. So back in the day in grade school, for example, you would get this is 12 over 2, so you get 6 units squared. And maybe that rough shape here might be those two things put together. Maybe it would come out to 6 or something like that. But that's not what we're really going to do here. I'm actually going to erase this just for now. That's just how we used to do area. It's like if you were to paint a space, how much physical space have you painted? That's what area means. It's square units, like little tiny squares. How many of these squares, if they're side 1, would we have? But we're going to let calculus do the work for us. We're going to do the integral, and it turns out the integral of a function from a point to another point, or an x value to another x value, is the area. So this is what we're working towards today. So area is the region, let me try to get this all on the page here. Area is the region bounded by 3 things. Basically the graph of f of x, so this line here, that's our function. The vertical lines, a and b, or x equals a and x equals b, that's these lines. It's basically start point and end point. So we can say x equals a is kind of our start, and a equals b, x equals b is our end point. Sorry about mixing up my words today. I always do that, but today is worse than usual because my brain is kind of in a fog. So please be kind, be gentle. Everybody love each other. And the x-axis. The x-axis being this. So I guess what I'm trying to say is if you were to, let me just make it really obvious. If you were to look at what the boundaries are, we've bounded by this wall, and this wall, and this wall, and this function, we want to know that area. We want to know how big is this red blob. That's the rule, or that's the goal of the day, is to figure that out. Okay? And that's what we're going to be working towards. It's actually much easier than it sounds. So here's the formula for the definite integral. Please don't get too scared of this. I'll try to break it down. So the definite integral, what it means is that the area of any function is the integral from a to b. Now you haven't seen these before. You haven't seen this notation before. But, you know, it's the integral of the function, just like normal. You need to integrate it, and whatever you get, you'll toss b into it first, and then you'll subtract whatever a is put into the function as well. So it's like a final minus an initial thing. So I should probably just put a little mini example here. Let's just say that I had the integral of something very simple like x. So this is what we've been dealing with so far. And we know that that would be x squared over 2, okay? And we'd have a plus c, but instead of plus c, we're going to have a boundary. Let's just say 1 to 3. And what we're going to see added to our notation is we'll have a bar that comes down, and it reminds us we need to input 3 and 1. Just hold on to your butts for a second. This will become clear in time, I promise. We're going to take the result, which was x squared over 2. We're going to put 3 into it. Okay, so that's the first thing we'll do. We'll put 3 into this, squared over 2. And then it tells us, so that's our 3. And it also tells us we're going to put 1 into that for x and subtract that result. I'm just kind of front loading this so that we get all the hard stuff out of the way. So the familiar piece is this. We've got the integral of something, and it should be familiar that its integral is this. But instead of having a c, which is reserved for when we do not know the function, we're actually doing what's called a definite integral, which means we do know the boundaries, and so the answer will be a result of substituting in these numbers. So we put a 3 in, we put a 1 in, and we subtract those two results. You'll get something like 9 over 2 minus 1 over 2, which is 8 over 2, or 4. So the answer to that would be 4 units squared, because definite integrals give area as answers. Okay, so that's like a little side note. Even if you didn't write that down, it's not the end of the world. I just wanted to give you a context for what we're doing, and everything we're going to do from this point on is going to use this idea where you substitute in two values. So back to the notes. Here are those steps in English. So these steps in English. What we're going to do when we get the definite integral follows these. These are the steps. First, we integrate the given function as normal, but write the result without c. So we're not going to have c. Evaluate the function by substituting the b value for x. So whatever this top value is, we'll put it into our function. whatever the answer was. That's what I did over here. Whatever the x expression was, we'll take 3 first, the b value, and put it into it. We can see that right here. And then the second step, whatever your a value was, goes into the function, which is this is the result of that. And then it says, as a number 4, subtract the 2 results. So I take my b version of it, my a version of it, and I subtract them. So that's my story. Hopefully that makes a bit of sense, but we'll do lots and lots of examples in this video, okay? So example 1a, finding the area using the definite integral. It says find the area under the curve. This is what we do when we are getting definite integral. That's what comes out of this. So in other words, if it says find the area under the curve, it's teaching you or suggesting that you use the definite integral. The function we're going to get the integral of is 2x, and our starting point and end points are 1 and 3. So I'll just get right to the point. The area is going to be, you don't need to write this part, but I'll write it for you, the integral from a to b of the function with respect to x or whatever variable you're given, okay? So you don't need to write that part, just that was there as a reminder. We can usually start by just writing what we see. So a equals 1, b equals 3. The function is 2x, and we're going to integrate it with respect to dx. So again, these are the new parts. That's the new stuff. Nothing else is really new. When you integrate this, you'll get 2x squared over 2, which is x squared. You can put that on the side of your page if you want, work that out, but it should cancel out and give x squared. Now we've got these new bars. This is new. We do have a new bar. It's called like an evaluation bar, I think is the name. It just tells us that we're going to sub in a and b, and you'll put b here and a there. I'll just use the colors that match up with my answer key here. So what we're going to do now is we're going to take this value, 3, and I'm going to toss that in for x. Oops, where'd my 3 go? Come back. There we go. Put that in for x, and I'm going to subtract the expression with that in it. Okay, b first, a second. So it's going to be 3 squared, because that's my expression with 3 in it, subtract 1 squared, because that's x squared with my a value in it. All right. Hopefully this is making a little bit of sense. Pause the video and take time to redo it yourself or think about it if you're having a little bit of trouble. But this is the whole story. 3 squared is 9, 1 squared is 1. 9 minus 1 is 8. That'll be 8 units squared. So we don't know how big these units are. Maybe they're meters squared, maybe they're centimeters squared. We don't know. But apparently this function, 2x, is going to have an area under the curve of 8 units squared. And I'm going to go ahead on the next page, example 1b, and show that this result does make sense for this function, but I'm going to show it visually. Okay, so pause the video here and finish the question up if you need to, and then I'll show the comparison. But keep this idea of 8 units in your head. So example 1b, it says proving that the definite integral gives the exact area under the curve. It says we're going to use geometry, which means working with the shapes, not the calculus, to find the area. So I'm going to look at this that I've been given, and I wouldn't make you do this on an assignment or a test. I just wanted to show this as a demonstration. We're going to try and see what the answer is if we use our geometry. Now the line here is 2x. Okay, so this would go forever. This would go up this way and this way. That is our line, y equals 2x. If you just take from these 2 points, a equals 1 and b equals 3, we can see hopefully that our region that we care about is bounded on top by the line 2x. It's bounded on the sides by a equals 1 and b equals 3, and it's bounded on bottom by the x-axis. This is the area that we care about, okay, inside here. I'm going to keep that empty for now. Basically, if we look at it in terms of geometry, it's essentially 2 regions, okay? We can think of it as a bottom region, just break it down into basic shapes. This is a first region, that's a square. And our second region is A2. That's a triangle. I wrote here that the area of a rectangle is length times width, and the area of a triangle is 1/2 base times the height. So area 1, our square region, is going to be length times width. We can see here on bottom that the length is going to be 2 and the width is going to be 2. So this is 2 times 2. And the area in total is going to be 4 units squared. Okay. Area 2, our triangular region, is going to be 1/2 the base times the height. We can see that the base is still 2. The height is actually 4. So it'll be 1/2 the base 2 times the height 4. And that will give us 1/2 of 8, which is 4 units squared. So the bottom is 4 units squared, the top is 4 units squared, and so our total area must be those added together, A1 plus A2. That would be 4 plus 4, and this gives us 8 units squared. This is an example that if we completely ignored most of the question and I just took, let me just show you something. If I gave you just this, you know, if this was grade school again, and I told you that this was 2 by 2, and I told you that this was 4, you could use just the square equation, or the rectangle equation, and the triangle equation, to find out what the area of this thing is. But in calculus, we can do calculus to find out. Let me put that back. My point is, look, we got 8 units squared. That's the exact same answers we got in the previous question. It's the same function with the same boundaries, and it gave us an area of 8. So the calculus does work. But in fact, the calculus is more accurate than doing it with shapes. So I've put a little note down here. Question. So why bother using integration if geometry works just fine? And the answer would be, geometry can give us the areas of simple functions, or simple shapes. These are simple shapes. It's a square and a triangle. But integration can give us areas for any function, no matter how complicated they are. They could be curvy, they could be all sorts of crazy stuff. Integration will do the heavy lifting for us. So in example 2, we're going to get a shape that is harder to do with geometry. Like you can see here, this shape, you could break it down into 2 pieces. Like for example, we could approximate this region to be like a first area. Let me make this a little easier to see. We could make this look like that could be A1. This is our first area maybe, and this could be another area, which you can see is kind of awkward. It's a little different to get an exact value for that. So it's just going to be approximation. I'm not going to get into the details, but if you look carefully at the scale here, this region is going to be about 10 units squared, and this region is going to be about 10 units squared. So in total, we should get about 20 units squared out of this thing. But really, you don't need to worry about any of that because we're doing the integration, not the geometry. I just wanted you to have a context. Okay. So find the area under the curve. That means get the definite integral of this function from x equals 2 to x equals 4. So this is our a value and this is our b value. So following our recipe for definite integrals, an area goes from a to b, so from 2 to 4, of the function, which is x squared, with respect to x. So I'm going to integrate that thing. I'm not going to get a c because I have boundaries. So x power 2 integrated gives x power 3 over 3. And put your evaluation line in. It's just a vertical line that goes down, kind of splits things up, and reminds you, put in a 4 and then put in a 2. All right? So using the same colors as in my answer key here, I'm going to put 4 in for x2, 4 in for x first, and then the 2 in. So say do this first, and do this second. And by do this, I mean sub it in. Okay, so the 4 goes into the x, or I should say the 4 replaces the x, it gets evaluated there. So this is a 4 cubed all over 3 minus the answer when you put this in for x, which is a 2 now. So 2 cubed over 3. These answers, it's okay to get fractions, by the way. This is a 64 over 3. minus an 8 over 3. If you work that out on the calculator, you should get 56 over 3 units squared. It's always units squared because integration of a definite integral in general, in the simplest case, gives square units. But that's a little bit tricky to understand. If you're not great with mental math, you might not know what 56 over 3 is. So it's totally fine to convert that to a decimal. It'll be an approximation because we'll have to round, but it'll give us about 18.7 units squared. So the moral of this story, I suppose, the takeaway, is that even though this was a quadratic function, which is harder to get the area of with basic shapes like these, integration has no trouble whatsoever. It gives us an exact answer. 56 over 3 is the exact area under the curve. So this would be an approximate area. It gave us about 10 per group, which in total gives 20. By the way, this would be because A is 2 here, B is 4, that's our boundary, but these, if you look at the boundaries here, this is a 20, which means it's 5, 10, 15, and 20, and you can see that the height of this thing, this would be roughly, I'm talking about the height of the triangle here, this would be about 10 units tall, this would be 5 units tall, this would be, let me make this in gray so it doesn't make it too complicated looking, this would be 2, so 2 times 5 for this rectangle on bottom would be 10 units, and this is 2 times 1/2 base times the height for this one, which is 10. I'm just showing you the geometry. It's totally secondary to the integration. This is not necessary for you to do. I'm just showing it for your benefit to know what the heck is going on here. If you had to estimate, it would be approximately 10 plus 10 units squared, which is approximately 20 units squared in total, but we can see that the actual exact area is 18.7, or at least 56 over 3. So at the end of the day, you actually could not write any of that triangle stuff. I'll actually show you what it would look like, just on the video, because why not, what it would look like if we only looked at the integration side of things. It would be the boundary here, and the boundary here, and the boundary here, and the boundary here. And we can see that this curvy line, this curved line here, is very difficult to get exactly unless you use integration, but the exact area would be 56 over 3 units squared. Okay, so that's honestly everything you need in order to do the rest of the questions in this course. All right. So what I'll probably do is write out the answers, but not explain them too much. I'll set them up and then I'll basically write them down without too much explanation, and probably fast forward the video as I do the workings, and you can pause as you want. So let's do it. Find the area under the curve, so that's the definite integral, and the curve is y squared. Between the lines x equals 1 and x equals 2, that means the starting value a, first boundary is 1, second boundary is 2, and we can see that here. That's a and b. So x equals 1 is a, x equals 2 is b. Those are our boundary lines. Let me just make it in red. First boundary line, second boundary line, bound by the curve itself and also bound by the x-axis. So essentially what the calculus is going to let us do is give us an area of a shape like this based on the scale that it's given us. Okay, so how many units squared we're going to have here. Come on, go back to where it was. I got to put it, sorry. So essentially we want the area of that shape that it's carved out for us. And the rest I'm not going to talk through. You can just see how I did it. So the exact answer is 7 over 3 units squared. And if you wanted to give a decimal answer, it would be about 2.3 units squared. And if you were to play the same game as I did before and try to toss some geometric shapes into this thing and try to get an approximate area, it would work out pretty well. In fact, if you just did the bottom box for the shape, it would be about 1 unit squared. And if you just did kind of the peak here, the triangular part, if you did the work on that, that would be about 1.5 units squared. So it would be about 2.5 units squared, which is very close to this 2.3, but not as exact as if you use the calculus. So hopefully that makes a little bit of sense. And if not, of course, you can still email me about any questions that you have. It might take a little longer than usual to get back to you. That's all I can really do. So I'm just trying to think if I've forgotten anything here. I don't think I have, so all right, I'll just move on. Find the area under this curve, y equals x squared plus 1, between the y-axis and the line x equals 4. So thankfully it gave us a picture. The y-axis is this one, right? And the x-axis is going to be this one already. And we want it bound between the curve and the y-axis, which is another way of saying x equals 0, and this point x equals 4, which is our b value as well, right? So essentially it's saying what is the area bound in this region here. But all we really need is to fill in our pieces. So the area is always going to be from a to b, in this case from 0 to 4, integrate our function with respect to x. And again, I won't talk out the process. The definite integral part is pretty easy now, or you should find it fairly easy. I will remind you, the y-axis is the point x equals 0, which means a is 0. So the rest I won't talk through. So I lied. I will talk about this part because we have two terms which have x's in it. And that's going to change how I do things. You might want to use brackets because look, when we subtract the result, both of these terms are going to be considered when we input something. So what I mean is if you just say subtract this, so 0 cubed over 3 plus 0, you're not going to get what you think you're going to get because this whole thing kind of came as a group. So in order to deal with that, you can either use round brackets or you can use square brackets. And it's very common when doing definite integrals to do square brackets, but it really doesn't matter. If you want to put a big pair of round brackets there, that would be totally fine. And we're going to evaluate this. Now because each of these terms has a 0 on it, that whole expression is going to go to 0. So I'm just going to say, boop, this is 0. If you don't trust yourself and you want to make sure that that is all going to go to 0, just put it in the calculator and you can convince yourself of that, okay? But this is going to be 4 cubed over 3, which is 64 over 3, plus a 4, and then minus a 0 here, so I'm not going to write it. 64 over 3 plus 4, if you put it in a calculator, is going to give us 76 over 3. That's an exact answer, so you should put units squared and put a box on that, and we'd be done with this question. Now, if you want to know in terms of more, human-like units what this means, you could pop out a decimal and round it to, 1 decimal place or 2 decimal places. It would 25.3 units squared. And there we go. So, based on this shape, if you were to do the same geometric kind of stuff as we did in the beginning, if you kind of broke this down into a box that was 4 by 1, and then you kind of tried to approximate this thing in terms of a triangle and did all that work, you should get an answer for that geometric stuff that's close to 25. But you would not need to do that. This is we're just doing the calculus, not the geometry. Okay, moving on to question 3. Just taking a look to see if there's anything new here. No, I'll just do all these. So I probably could just leave the rest for you, but I'd rather get it all done. So if you need my help, you've got it, right? So find the area under the curve, which means get the definite integral of this between the lines x equals 1, which the first boundary is a, and x equals 2, so the second boundary is b. That means the area is the integral from 1 to 2, which we can see down here, of the curve x cubed with respect to x. This is the function x cubed. You can kind of see it mapped out there. It's got a little tail here, which means it is a cubic function. You could toss it into Desmos, and I would do that if I had a little more time or a little more energy. So the definite integral of this, x to the power 4 over 4, we don't get a c, we get an evaluation bar. It tells us to put 2 and 1 into this. So you can see in the answer key I've color-coded it, but just in the interest of time, This gives 2 power 4 over 4 minus 1 power 4 over 4. Simplify that down, it gives 4 minus a quarter. And if you work that out, it's 15 over 4 as an exact answer, 15 over 4 units squared. So that would be a perfectly fine answer. And if you wanted to do it as a decimal, it should give 3.75 units squared. Also a perfectly fine answer. Not much to say about that. Moving on. Find the area between the curve and the x-axis over the indicated interval. The only real trick in this question is we're going to have a negative for one of the x values that we substitute in. So just be really careful with your brackets. I've wrote this in the answer key, but I'll add it here. So you want to use brackets when substituting in a negative. Sorry for my writing. It says use brackets when substituting in negatives for x, because if you don't use brackets with the substitution, you're setting yourself up for possible errors. So the area is the integral from a to b, so from -4 to 4. If you're not sure about this, that's because a is -4 and b is 4, of the function that we've been given, which is 16 minus x squared with respect to x. So I'm going to write out the integral here. That would be 16x minus x cubed over 3. Put the evaluation bar in. We're going to go from -4 to 4, putting in the top one first and putting in the bottom one second. Now, it's not that bad, but you got to be careful. We just need to make sure we put in this one first in for these two x's, and then do the same thing with the -4, right? So this is 16 times that 4 minus 4 cubed over 3. I'm going to put all that in square brackets because I am going to need to do the same thing for the -4. So minus the whole expression with -4 in for all those x's. So 16, this is the brackets I'm talking about for the negatives, okay? Those red ones there. If you didn't put that in, it could be a problem later, depending on the question. So just any time you put negatives in, really try to focus on putting brackets on it. And that should make your answers come out nice. It doesn't matter for cubes as much, but if this was a square, like if this power was a square or a power 4, power 6, any even power, your powers would mess up the sign. You'd get negatives or positives when you're supposed to be getting the other. Anyway, if you work out these brackets, take a moment to work them out, you should get 128 over 3. So you can pause the video and try that if you want, minus a -128 over 3. And what that gives us, those two signs combine to make a positive, right? And so it's really 128 over 3 plus 128 over 3, which is 256 over 3. And that would be units squared. And that, as a decimal, would be 85.3 units squared. So the takeaway in my book for this question is anytime you have a negative, use brackets, and be very careful about how to set these things up. I know there's another thing I was going to say for this, but I just can't keep my brain on straight today. Like I said, I'm kind of in a bit of a fog. So if I'm saying anything, if I'm making weird mistakes and not catching them myself, you're just going to have to forgive me. It's been a long weekend kind of thing. But let's see, anything missing? No, that's all I can think of. I can't think of what I was going to say. So. Number 5, find the area under the given curve. Now this integration is going to involve the integral of a square root. And so you need to be careful about square roots. You got to rewrite them before we start. Might be a good idea. So you don't need to, but it's a good idea to at least consider that that is a power of a half, right? And then it says from x equals 0 to x16. So that's our a value, that's our b value. And we'll just go ahead and get our area, which is the definite integral from 0 to 16 of our function. So integrating this should be a joke for you at this point. If you've been keeping up, you've been doing your practice, it shouldn't cause you too much issue, and I hope it doesn't. It'll give you a power of x to the power of 3 over 2, and then the reciprocal comes to the outside, because we're dividing by 3 over 2, which means we're multiplying by 2 over 3. Plus 6x. Don't add a c. Instead of a c with definite integrals, we have a bar, which puts in our evaluations, right? So we're going to have 16 go in first, we're going to have 0 go in second. So this should look like this. 2 over 3, going to have 16, power 3 over 2, plus 6, with 16 in for x, minus the same thing, but with 0 in it. Almost missed a few things there. So there is an error here, and I want you to take a moment to look at this and see if you can catch it. It's brackets. Okay, it's very important. These brackets are important, but not so important. These brackets on the second half, where you're subtracting, are very important, because there's a plus in front of this. It doesn't affect anything, but this minus very much does affect things, because it's going to change the sign of everything inside of that. So make sure you use the brackets, and you'll be okay. Now in this case, if you're paying close attention, these are both 0. So anything multiplied by any kind of 0 is going to get deleted. So that whole thing is going to go to 0, and we only really need to worry about this result. But if you're ever in doubt or you don't trust your own calculations, just do the whole thing out and show yourself that it goes to 0. This expression here gives us a 416 over 3 units squared. And as a decimal, how many square units that really is 138.7 units squared. Give or take a few decimal places. And there we go. So we've got 3 more pages. The next page is an extension. I'm actually just going to please see the answer key for this one. I did kind of answer key. I did an explanation of this question in the assignment walkthrough video, so I'd prefer you to take a look at that. So see assignment 6 walkthrough video for that. I posted a question that involves subtraction of the areas, and you can go ahead and watch that video if you want, or look through the answer key. There's nothing crazy going on in this question, but just in the interest of time and saving a bit of energy for me, I'm going to ask you to take a look at that. If you have questions that remain after watching the video and looking at the answer key, get in touch and I can help you out then. But I wouldn't ask this question on a final or on the test. Speaking of which, the test won't cover, I don't think it'll cover this material. I might actually stop at last class's material. So that would be, let me look at the pages, U substitution. The test covers up to and including U substitution. Okay, I'll probably write an email about that. Okay, last topic, and a very short one it is. Integration is more than just the area under a curve. So the definite integral can give the area under a curve, as we've seen, but that's not all it can do. Integration has a huge range of practical applications. So these include many things, most of which we're not going to touch on. I just want you to know this moving forward in your career sort of thing. Integration simply reverses the derivative process. That's one of the first things we learned in this unit. So if that's the case, it can allow us to find the displacement of an object if we know its velocity. Because remember, displacement s and velocity, if we go one way, we can reverse it and get the integral and get back its displacement. So we can start with velocity and move our way back to displacement. So we reverse it. We can find the velocity of an object if we know its acceleration, because if we know its acceleration, we can reverse it, go back to velocity. And some new ones that I've added here, the work done on an object if we know the force applied, the mass of a linear object given its density, and even the amount of charge that is past a point if we know the current. And I'll just give you the formulas in these next 2 pages, and you can see yourself that these formulas do work. Okay? So generally speaking, if we know the formulas for a given situation, we can apply what we've already learned to get practical results. So let's just start with question 1. We'll do the other 2 questions on the next page. Application. Stopping distance of a train. The driver of a train traveling at 20 meters per second applies the brakes, and then the velocity decreases by 1.25 meters per second every second. And it says, find an expression to represent the velocity as a function of time. So in the interest of time, I'm going to just set this up for you. On a test, you wouldn't need to set this up yourself. But based on the question, how do we find velocity? See if you can think about it. How would you set up velocity for this question? Pause the video if you need to, and take a moment to see if you can get this equation yourself. All right, I'm going to assume you pause the video. What we're going to do here, the expression of velocity is going to be basically the starting velocity, or the initial velocity. Subtract the rate of velocity times the time that it took. So sort of like referring back to a previous unit, way back to functions. We can build our own thing. So really that's my mental process, how I would approach this question. And essentially what this breaks down into is 20 is our starting velocity, minus 1.25 meters per second every second. So our full answer for the velocity expression is going to be this. Now I would probably give that to you on an assignment, but for this particular case, you had to build it yourself. But once we have that expression, we can go on and do part B. Part B says the train takes 16 seconds to stop. Find the distance d traveled during this time, and it gives you the formula. It says that the displacement is the integral of the velocity equation with respect to time. A is the start time, B is the end time. The start time, if you start a stopwatch, it's t equals 0. And B, the end time, is going to be t equals 16. So those are the things that I'm going to put in to my boundaries there. For example, this will be the starting value and the end value. That's what I'll put on the integral, okay? So to bring it all together, displacement is the integral of the velocity, which is 20 minus 1.25 t. Notice it's not x, it's t. So don't let that, make you lose any sleep. We're just matching the variables. So if you don't have x's, just make it all t's. And the starting time was 0 and the end time was 16. So take a moment to pause the video if you need to and really think about this, see if it makes any sense to you. But ultimately, the integrals I'm going to make you do are not going to be very large. This is as hard as it gets, really. Now, integrate that. So you get 20t minus, and then this is 1.25t. T is going to get a square, and I'm going to divide by 2. So the expression I should get from this is this. You can do that on the side if you want. Essentially, it's 1.25t squared divided by 2, right? If you divide those out, you get 0.625t squared. So that's where that comes from. And evaluate it from 0 to 16. So take those values, put them in for t, and you'll get what you need. And if you're keen, you're paying attention, you'll see that these are both 0. Things times 0 give 0. So this whole expression could be 0. You could have actually essentially not written any of this and just put a 0 there, and I would be okay with that. But you should show some evidence that you know it's going to go to 0. And then this first bracket should evaluate to 160 meters, and you'd be done. Now this isn't square units in this case because we're not talking about area. We have a specific case where we're given a new formula which gives distance or displacement, which the units for displacement are meters in this case. So that's why it's not units squared. And that's it. That's kind of the sorts of things we're going to do now. We've got 2 more questions, and then it'll be the end of the entire course. So if you've understood it so far, you basically have another couple minutes, and the nightmare will be over. Application: work done to a spring. A force is applied to a spring to stretch it 0.5 meters from its initial position. Initial position would be 0 generally. The force applied can be represented by the function f of x equals 50x. So our function is 50x. How much work is done to stretch the spring? The work is the integral of the force. So A is the start position. If that's the case, then A is going to be 0. B is the end position, which is going to be 0.5 meters. So if you're having trouble with the speed at which I'm going through this question, I would like you to pause the video and kind of take a moment to read the question yourself. See if you could have pieced this together yourself, and then rewatch it or continue from where you left off. And if you just can't grasp it, please email me. I will absolutely try to get back to you. I'm just going through this as quick as I can just to have the video done. So the formula for work is work equals the integral of the force from A to B. So the work is going to be the integral from the starting position 0 to the final position 0.5 of the force equation, which is 50x, and the variable here is x, so the integral is going to be with respect to x. If you do that integration, it'll be 50x squared over 2, which is 25x squared. Don't put a c, put your boundaries instead. So once again, this is your 0.5 as your b value. Your a value is going to be 0. So at the end of the day, it's going to be 25 with 0.5 in it squared minus 25 with 0 in it squared. Might as well color code it just to have some fanciness at the end of the course here. And anything times 0 is 0, so that's gone. And at the end of the day, I've got basically a quarter of 25, which is 6.25 joules. Now, you wouldn't necessarily know what the units for joules are, and there are different units for work. Sometimes it's called Newton meters, other times it's called joules. Really, I just wanted the number, but if you happen to know what the units for work are, you can go ahead and call it joules, which is why the answer key has a J there for joules. Last question. Let's see if I can make it. Application: mass of a thin rod. Consider a thin rod oriented on the x-axis over the interval 1 to 3. So essentially this is the situation. The density, which means the mass per volume of the rod, changes as we move along the rod according to the function density is 2x squared plus 3. So what this means, this is our rod here, okay? It means that it's got a very low density around this point here, and as we go along the rod, it gets more and more dense. So we've got basically not much material to it on one part of the rod, and it gets thicker and thicker as we move on. Maybe this rod was pulled and stretched out or something like that, but it doesn't really matter. The idea is that essentially from like 1 to 3, which is the interval a to b, we want to know what the mass is even though the density is changing from this part. And the density changes according to a formula. You actually don't need to know a lot of the specifics about the question because the math kind of does it for you. The mass, m, of a thin rod is given by this simple integral. So it says it's the integral of the density with respect to the x. So the mass is going to be the integral from your start to end point, which is going to be from 1 to 3. The density equation is 2x cubed plus 3, and we're just going to integrate it with respect to x. And the rest is essentially business as usual. Integrate this thing. This is going to be 2x to the power 4 over 4, which is the same as 1x cubed over 3. Check that yourself if you don't believe me. Sorry, it's, let me see. No. It's, I'm glad I checked this. This is 2x to the power 4 over 4, which is going to be the same as 2x to the 4 over 2. So I've got an answer, I've got a mistake in my answer key. I'm going to just jot down here. Couldn't get through a whole class without a typo. So there's a typo there. And plus 3x evaluated from 1 to 3. And let's go ahead and give them some colors, just to end it on a fancy note. So I'm going to put in 3s, I'm going to put in 1s. There's no 0 here, which means nothing's going to disappear. And see what I get. So this is 3 to the power 4 over 2, plus 3 to the times 3. I've got two terms, which is always safest to put in square brackets, minus, definitely a good idea to put square brackets when you got a minus here. This is 1 to the power 4 over 2. Plus 3 times that 1. And if you're still wondering where those numbers are coming from, this is our b value. B goes in first, kind of our final, and then our a goes in next, which is kind of our initial value. And I'll need to recalculate these because my key had a typo in it. Let me just see what this would be here. So 3 to the power 4 all over 2 plus 3 times 3. I've got 99 over 2 for this one. Minus 1 over 2 plus 3. Oops. Let me just 1 second here. I'm doing this on the fly. Plus 3. So minus 7 over 2. So by my calculations, I've got 92/2, which is 46. And the units would be kilograms because it's mass. Now I'm going to pause the video for a second for me and see if I've made a mistake here, just because I don't want to lead you down the wrong path, and I'll be right back. So I did make a mistake, but it wasn't the mistake that I thought it was going to be. In fact, the answer key was right. I just misread something. And you probably screamed this at me, and I'm sorry, and infinite apologies. This was a 2, which is a 2. All right, so I made a mistake. I read it as a 3, and then everything kind of went from there. So not a big deal. I'm going to be adding 1 to that. I basically need to redo the question as if that was a 2, because that's what I started with. So it would give me a 3/3 here, which would make this still a 2 in front, because that 2 hasn't gone anywhere. Let me color code it so that you can follow my story of Typo. That's 2, so it's going to be 2 times 3, power 3, over 3. And that would also be a 2 here, times a 1. Sorry about this. It might be just easier for you to pause the video and make the changes yourself. But that's a 3, so 3/3, 3 there. That would give me, my first bracket should work out to a 27 in this case, assuming that I haven't made any issues. And again, this one gained a 2, so be careful when you calculate that one out. That should give you a 11/3 by my calculations. If it doesn't work out for you, please let me know. And the final answer, instead of giving that nice clean answer, it's actually going to be a fraction, 70/3 kilograms. And if you want that as an exact, or at least a decimal answer, 23.3 kilograms is about the mass of this rod. So sorry about that. My mistake, of course, but the logic was alright, and if you made that mistake yourself on this, I would only take off probably a mark. I'm pretty lenient when it comes to that, because we all make mistakes, we're only human after all, but I want you to get the logic. And in summary for this, the logic was, the formula for the mass of a thin rod is this. A and B are your starting and end points when you look at the rod and say, where is the region that I care about? What's the interval I care about? So I care about A being 1, B being 3. That was given by this interval up there. If you integrate the formula you were given, you get this. You put in the 2 endpoints, 3 and 1, and you'll get the expression below, right over here. And then if you're careful, unlike I was, if you're careful, you should get the answer that I got. And that, ladies and gentlemen, and everything in between, is the final page, final topic, final unit, final everything for this course. From now on, everything is review. And I really hope that I'll be able to do a review video for you for next week's test. Test being on Monday, April 11th, I believe. Yeah. And I'll also do my best to have live review classes for the final exam, but I'll keep in touch with you in that case. So, thanks for watching, and if you have any issues with it whatsoever, please get in contact. And other than that, I wish you all the best. Bye-bye.